Okay, so we're going to wrap up the 2019 AB free response test here with number 6. And there's a whole lot going on in this problem. We've got limits, we've got chain rule derivatives, we've got product rule, we've got L'Hopital's rule, we've got a theorem called the squeeze theorem that doesn't come up in the AP test too often. So a lot happening here, so let's dig into it. Alright, so we start off with three functions, f, g, and h, and we're told that they're twice differentiable. Now, if they're differentiable, that means we automatically know that they're continuous, and that's going to be a really big deal in this problem. So we've got differentiable and continuous functions. We know the value of the functions of g and h at x equals 2 is 4. And we also have a line that's tangent to both of them at x equals 2. And that tangent line is going to play a big role, especially here in part A. So speaking of part A, it asks us to find h prime of 2, which normally you would just derive a function and plug in 2 and get your answer, but you notice, of course, that they didn't give us an actual function for h. So we can't do that, which means we need to look at other information we've been given. Specifically here, that information is in the form of a tangent line. Because what we know about a tangent line is that the slope of the tangent line is going to be equal to the slope of the function at our given x value, which is 2. And so the slope of our function, or the derivative of our function h at 2, is going to have the same slope of this line here that is tangent to h at 2. And looking at the form of this tangent line, we see that 2/3 is our slope. This is just point slope form is all it is. You know, you've got y minus your y coordinate, and that y coordinate was moved over here to be 4, x minus your x coordinate, and this is your slope. So our slope of this tangent line is 2/3. The slope of that tangent line is going to be equal to the derivative of the function at 2. And that's all we say here, is that the derivative is equal to 2/3. There's really not any work for you to show because it's all right there laid out for you in the tangent line. There are no derivatives to take, so you should simply be able to state that in this problem and get full credit. Alright, moving on to part B. We're given a new function a and told that it equals 3x cubed times h of x. We need to write an expression for the derivative of a and then find a prime of 2. So starting with the derivative, this is going to be a product rule question. We've got two functions here. We've got 3x cubed and we've got h of x being multiplied together. So we're going to use product rule to derive those. And this is what that looks like. The way I do product rule is I take my second term, which is h of x, and I multiply that by the derivative of our first term, which is 3x cubed. And the derivative of 3x cubed is going to be 9x squared, plus the first term, which is 3x cubed, times the derivative of h, which is h of prime of x. We don't know that value yet. Well, actually we do. We found it in part A. So let's go ahead and substitute 2 into this function. So a prime of 2 is going to equal h of 2 times 36. I just plugged in 2. 2 squared is 4, and 4 times 9 is 36. Plus, if you plug in 2 here, 2 cubed is 8, and 8 times 3 is 24, times h prime of 2. And so our final step then is going to be substituting for h of 2, which they told us in the initial prompt was equal to 4. And then plug in h prime of 2, which we found in part A. So if I plug those in, you've got 4 times 36 plus 24 times 2/3. You simplify, and you get 160 for your answer. One note that I do want to make here is that h prime of 2 depends on your answer from part A. And what if in part A you weren't sure about your answer for h prime of 2? In fact, maybe you're confident that it's incorrect. That does not mean that you can't get points here in part B. Just because your answer in part A was incorrect, you're still able to show here in part B that you understand the concept of product rule, that you know how to evaluate a derivative at a point by plugging in that x value and by simplifying. So even if your answer from part A was wrong, let's say you got h prime of 2 was equal to 8, and you plugged in 8 right here, and you simplified. Yeah, you're not going to get 160, which is the right answer to this question, but you're going to show a lot of good work in here that demonstrates that you know some math and some calculus, and you're going to get some points for that. So just to encourage you, if you are in part A of a problem or any part of a problem and you don't quite know what you're doing, that doesn't mean that you're automatically out for the rest of the points in the problem. You can keep going. So whatever you got in part A for h prime of 2, use that number here and get some points, whatever points you can get. All right, part C is where this gets more interesting. We have function h that satisfies this equation here, and it is known that the limit of h approaching 2 can be evaluated using the L'Hopital's rule, and that tells us all kinds of things. Use the limit of h as x approaches 2 to find f of 2 and f prime of 2 and show the work that leads to your answers. Okay, so first things first. If L'Hopital's rule applies, one thing we know is that it only applies when we get an indeterminate form by substituting a number into our function. If you don't get an indeterminate form, then you can't use L'Hopital's rule. So they've told us L'Hopital's rule applies, which means that if I were to plug 2 into this function, I should get 0 over 0. Otherwise, L'Hopital's would never come into the situation at all. So obviously on the top I get 0 because 2 squared is 4 and 4 minus 4 is 0. But I also know that on the denominator I should get 0. And that's what this next step is showing. Therefore, 1 minus f of 2 cubed should equal 0. Looking at that, I know that 1 minus 1 equals 0, which means that this expression here, this f of 2 cubed, has to equal 0, or 1, excuse me. And the only way that's going to happen is as f of 2 itself equals 1. That would give you 1 minus 1 equals 0. So we've answered half the question already. They wanted us to find f of 2. F of 2 has to be 1 in order to get the 0 over 0 indeterminate form. And so we've got half of our question done. Now the next thing about L'Hopital's is it says that as long as your form is indeterminate, what you can do is take the derivative of the numerator and take the derivative of the denominator and then take the limit of that as x approaches 2, and you should get the same answer as the limit of h when x approaches 2. So that's what you see me doing here. We know that the limit of h of x as x approaches 2 should be equal to the limit as x approaches 2 of the derivative of the numerator and the derivative of the denominator. So on the top here, we're saying that the derivative of x squared minus 4 is equal to 2x. And on the denominator, that's a little trickier. The derivative of 1 is 0, so that's gone. For f of x cubed, you're going to bring the 3 out front, which gives you a negative 3. You subtract 1 from the power, which gives you f of x squared. And then you multiply by the derivative of what's in the parentheses. So you multiply by the derivative of f of x, which is f prime of x. So that's chain rule happening there. And then you would substitute 2, and 2 times 2 is 4. On the bottom, if you plug in 2, I know that f of 2 is 1, and 1 squared is 1, so I just get negative 3 here, and I get negative 3 times f prime of 2. Now, I said all of that equals 4, and the reason I know that is because they said earlier that h was a continuous function. And if it's continuous, that means that the value of the function, which they told us h of 2 is 4, should be equal to the limit of the function. So if the value of the function is 4, that means that the limit of the function as x approaches 2 should also be 4. And that's how I know that I can set this limit here equal to 4. From this point forward, the only way for this equation to work is if f prime of 2 is negative 1/3, because negative 3 times negative 1/3 will multiply to be positive 1, and 4 over 1 gives me 4. So that allows me to answer the question that f prime of 2 is equal to negative 1/3. Now, if you were a little confused at that part where I was talking about continuity and the value of the function equaling the limit of the function, that's exactly what we're going to talk about in part D, so hopefully we can clear that up a little. So in part D, it is known that g of x is less than or equal to h of x on this interval. So all that means is if you were to graph these two functions, h would always be above g, unless perhaps they were equal to each other, which means h and g would be touching at that point. Then we have k as a function that is in between g and h for x is 1 to 3. Is k continuous at x equals 2? Justify your answer. So the first thing we need to talk about is this idea of continuity. You don't have to write this on your response, but as a reminder, there are 3 things that are required for a function to be continuous at a point. So specifically for function k at x equals 2, the first thing that must happen is that k of 2 must exist. There must be some point there, some actual y value when x equals 2. That means there can't be a vertical asymptote at 2. There can't simply be a hole in the graph at 2 unless there's a point above or below that hole. But whatever the case, when x equals 2, k has to have a y value. The next thing is that the limit of k as x approaches 2 must exist. That means that as you approach 2 from the left and right, you've got to be approaching the same y value from both sides. And then finally, whatever k of 2 is, and whatever your limit is, in order to have a continuous function, those two things must be equal. So whatever the y value is at 2, your limit then, your function has to approach that y value from the left and the right. So the function has to exist, the limit has to exist, and the value of the function and the value of the limit have to be equal. All three of those things have to be true for us to show that k is continuous. Okay, so let's start off talking about g and h. They told us in the original prompt that g and h were differentiable, and I told you that means that they are also continuous. So I know I've got two continuous functions, which means that for g and h, all three of these things have to be true. They told us that g of 2 and h of 2 were 4, so that means that g of 2 and h of 2 exists. And if it's continuous, I know that the limit also exists, and that the limit must be equal to the value of the function. So if the value of g of 2 and h of 2 are 4, that means that the limit of g of x and h of x as x approaches 2 must also be 4. Now, why are we setting all of this up? Well, think about the graphs. Think about g being below h. Except for at x equals 2. What's happening at x equals 2 is that those two graphs are actually touching, and they're touching at a y value of 4. The reason that's so important is because k, we know, is in between g and h. And so if h comes down to y equals 4 and g goes up to y equals 4 when x equals 2, and k is squeezed or sandwiched in between g and h. What that means is that in order for k to squeeze in between g and h, that means it must also be equal to 4. It must also approach 4 in order to fit in between g and h. So if your bottom function is touching your top function, then whatever function is in between those two has also got to touch to squeeze through at that point, and that is something called the squeeze theorem. And so that's what we're talking about here. We're saying that since k is in between g and h on 1 to 3, then by the squeeze theorem, k must also be approaching a y value of 4 when x is approaching 2. There's no other way it could happen in order for it to fit in between your bottom function g and your top function h. So what I've established here then is that the limit of k exists, which is our second bullet point, and that it has a value of 4. The other thing that must be true then is that k of 2, the actual value of the function, has to be 4, and that has to be true if you've got this picture of the graph in your mind. If the function on the bottom equals 4 and the function on the top equals 4, then the function squeezing in between them also has to be equal to 4 when x equals 2. So if we've established that the limit is equal to 4 and that the value of the function is equal to 4 and they both exist, then we've satisfied all three of these bullet points and all three of these requirements for continuity, and we can state that therefore k of x is in fact continuous at x equals 2. Now that seems like a whole lot of work. I know that's what my students felt after they took this test last year, and it is, but it's important. You know, the squeeze theorem is something that you can understand and use, and the idea of continuity especially comes up a lot. You need to understand what it is that is required for a function to be continuous at a specific point. Now, the good news, if this feels overwhelming to you, is that it was only 1 point on this particular question. So out of the 9 possible points, only one of those points came from part D. So if you didn't quite make your argument in a very airtight fashion and you didn't earn this point, it wasn't the end of your AP hopes on this question. It was only 1 out of the 9 points, so you can still do perfectly fine on this question. And that's how most free response questions work. Keep that in mind as you're working through these problems. If there's one part that's just a mystery to you, that's okay. If you're getting the other parts of the question, you're going to be fine. But at the same time, every point counts. And so if you're able to understand the concepts of continuity and understand the idea of the squeeze theorem, and you're able to get this last point, then all the better. But that should be it for number 6. As always, if you have any questions, please, please, please reach out to me and ask for help, and I will do everything I can to help you out. And I'll see you again soon. Thanks, everybody.